All right, so we've talked about organolithiates, one type of organometallic reagent, and now we are moving on to Grignard reagents, another type of organometallic reagent. And as you can see from the notes that you have and also from the board here, we are using magnesium instead of lithium. So how does that change things? So if you look at a periodic table, you have lithium right here, hydrogen's above that, and magnesium is right here. So essentially, as far as the differences in these elements, this is group 1, this is group 2, so this has 1 valence electron, this has 2 valence electrons, but their electronegativities are going to be remarkably similar if you think about it, because electronegativity increases that direction, and since these are staggered like that, they have very similar electronegativities. What's the major difference? The major difference is magnesium has 2 lone pair or two electrons instead of 1. Essentially, how do we make these Grignard reagents? Again, we have an an alkyl halide. So we're doing phenyl Grignard here. In the note packet, it has that phenyl drawn out as a benzene ring, but we're just going to do the pH up here. It's the same idea. And essentially, it's the same kind of mechanism that happens with a lithiate. Lithium wanted to get a full octet. How did it do that? It gave up 1 electron. What's magnesium going to do? It has to give up 2 electrons. So it's going to be the same process where we kind of undergo radical chemistry, and that generates phenyl radical plus Mg has a single lone pair, or single electron, which makes it positively charged. Br is negatively charged. They're going to hang out close to each other. And then essentially these two are going to combine. And that makes phenyl negatively charged. It's got a lone pair making it negatively charged. It makes Mg 2+, and then we have Br minus. So that whole piece together is a neutral. And people often draw Grignards instead of in this ionic way, they draw them phenyl MgBr. That's not incorrect, that's not incorrect. But I think the two ways that people draw them most often is with this covalent bond or with pH negative, so whatever the R is negative, and then MgBr plus. This complex together is 1 plus instead of the 2 plus minus. So that's how people generally draw them. As far as how do they react, this is going to look a lot like a lithiate, right? It's essentially an anion on a carbon. That's not going to be very stable. So Grignard reagents and organolithiates can actually be used interchangeably. And really what that means is in our class, someone might choose in a synthesis question to use phenyl lithium. Someone else might choose to use phenyl MgBr. Does it matter? No. Those would be equivalent answers in a synthesis type question. Where does it actually matter, organometallic, organolithiate versus Grignard reagent? Really the differences between these two reagents are nuanced. So what does that mean? In an actual laboratory, when you're running reactions, the Grignard might give you a different yield than the organolithiate. But those are things that are nuanced. It's hard to really know what the answer is going to be until you run the reaction. So that's why we teach both, because in many cases, one is better or the other one's better in the lab. Again, it's not possible to know which one's going to be better until you try it. So that's why we learn both. Organolithiates, it's a really nice name. It's like organic with a lithium, organolithiate. Grignard reagents, it's a little bit more annoying. Grignard, it's named after a chemist. So that's something you just have to kind of click in there. So Grignard reagents, magnesium, organolithiates, lithium, but pretty much the same idea. So now we're going to see some used in a reaction. All right, using Grignards or organolithiates in a synthesis question, sometimes we'll see them, like we'll just start with the organolithiate, and sometimes we'll generate the organolithiate or the Grignard. So we have a synthesis type predict the product question here, 3 different things. So maybe pause the video and try to predict the product. You did it. Now we're going to give you another shot at it. So again, there's 3 reagents. There's going to be 3 things that are formed throughout the process of this reaction. One will form one thing. Once we add the second reagent, we'll have another intermediate. And then we would add that third reagent to get to the final product. So again, if you haven't done this already, pause the video right now and show how the product that you predicted would have formed based on the multiple steps. And it never hurts to draw mechanisms. Mechanisms are a great way to kind of understand what's happening in the reaction. So take a minute to try that out. All right, back at it. So what happens when we treat an alkyl halide with magnesium? We form that Grignard reagent. So the single electron transfer process is going to happen, the radical chemistry, and that is going to give us our Grignard, MGBr on there. We could have drawn it like that. You can also draw it like this, where we have a lone pair on that carbon, and then we can draw MGBr plus. So whatever way makes you feel most comfortable. I think more often in the textbook you're going to see it drawn as a covalent bond, but I actually think that drawing it as an ionic bond makes the chemistry that they do more intuitive. So I kind of prefer this drawing method for the purposes of this class. So what happens when we add this Grignard to that? Well, the negative is going to flow to the positive. The positive is that carbonyl carbon. I'm going to draw it right here, just so we can kind of see how that happens. I turned it over, but essentially, negative is going to flow up there, and we will form our oxyanion intermediate. So we have our carbons of our Grignard reagent. This carbon made a bond to that carbon, so we'll draw a bond to that carbon. That carbon is still attached to that carbon. And then we have our O minus there. Is this the best description of this intermediate? Is there something that we could do to add to this to be more descriptive? Yeah, we could, right? Because this is not indicating stereochemistry here. Are we going to have it be the wedge or the dash or both? It's going to be both, right? Because that Grignard could add to the front, it could add to the back. So we'll draw our wavy guy here, indicating that it is a mixture of enantiomers at this point. That would be the product of our second step. Then we're adding our acid as our third step. That's our H3O+. That is a strong enough acid for this strong-ish base to grab a proton. And now we have our product, which is the secondary alcohol. That's how we can form the Grignard in situ from the halide, the alkyl halide, and the metal. And then we used it in the second step with a ketone or an aldehyde. One thing that would have made this better, and I need to be better about doing this for you all, is to think about solvents. What solvent did we need for this first reaction? We needed an aprotic solvent. So we can't use something like methanol, like water, because this would react immediately with that solvent. So one thing that we could use is something like diethyl ether. So that's what we'll draw up there instead. So that finishes that one. All right, so bottom of our examples on the page, we have right here. So what's going to happen here? Go ahead and predict this product, and then we'll come back to this together. All right, you paused that you did that. You're back now. So I think that a lot of you, upon doing this the first time, are going to say, oh, Grignard reagent, what do we know that they do? They add to carbonyls. Boop. But what did we also say? We said that with these organometallic reagents, with acetylide ions, with lithium aluminum hydride, we have to use aprotic solvents. So let's draw that in too. So we'll use something like diethyl ether that has no acidic protons. Why did we have to do that? We had to do that because if there are acidic protons around, proton transfers are faster. So is there something that's going to prevent the nucleophilic addition to that aldehyde on this molecule? Yes. What is it? It's this OH, right? We said we can't use something like water. Well, this functional group on this molecule is just like water or an alcohol. It has a pKa of around 16. So if we add our organomagnesium bromide, or our Grignard reagent, to this reaction, instead of it adding to there, so that's what we thought it was going to do. It's not going to do that. Instead, it's going to grab that proton. So if we mix these two reagents together, 1 and 2, all we're going to get as the product of that first step is the anion will now be on that oxygen. What happens in the next step? 2, we added H3O plus. Well, that's just going to reprotonate our alcohol, right? That would reprotonate our alcohol, and we would get back the starting material. This would be the exact same thing there that's over here. So this just is an example that shows that we need to ensure that there are no acidic protons around when we are using these organometallic reagents. If there are acidic protons around, a proton transfer will happen instead. So essentially, we can't use these organometallic reagents in the presence of acidic protons or functional groups that have acidic protons like alcohols. This has to be used in the absence of those sources of H+. So the last thing on the page said, when using organometallic reagents, always ensure no proton transfer reactions can occur. And then it says, a very important point, acid-base reactions are the blank chemical reaction. And they are the fastest type of chemical reaction. So that's what goes in that blank. Acid-base reactions are the fastest chemical reactions. They have very low energy of activation barriers. So if there is a downhill acid-base reaction that can occur, it's going to occur faster than a nucleophilic addition, than a substitution reaction, than any of those reactions. So we always have to be cognizant of using aprotic solvents with these and ensuring that the substrates themselves, the starting materials, don't have any acidic protons on them as well. Well, then how are we going to do it if we want to make that? Well, we're going to have to use something called a protecting group. And that we'll see what that means very shortly. So get excited about that. Yay!